who will tell us about the proof complexity and total search problem in problems in NP, I think.
Okay. Video. Yeah, so thanks for inviting me to the seminar, and also thanks for inviting me to give the first talk. Hopefully it'll be, hopefully I'll wake everybody up. Okay, so I'm going to be giving a survey talk on connections between TFNP complexity. And I'm going to be going slow, and I'll remind everyone to please ask me any questions. I think that a lot of what I'm going to talk about, probably half of this room is very familiar with, and maybe the other half is not so familiar at all. So definitely don't be afraid to pause me or ask me questions, or give me corrections if I'm saying something slightly out of order. Okay. Okay. So to start off, let's begin with a little bit of an introduction to TFNP. So let's start with the basics. So throughout, we're gonna start by letting R be an NP relation. Okay, so this means that it's polynomial time computable and also polynomially bounded, right? If there is a certificate Y witnessing the relation, then there's a small one. Okay, so associated with any NP relation, we have this natural search problem, right? Which we kind of, in the typical theory of NP completeness, at least when you teach it to undergrads, you kind of ignore it a little bit, right? So what's the search problem associated with it? Well, you're given some input X, which we think of as an input to the left part of the relation. And the goal is to actually output a certificate Y such that XY is in the relation, right? Not just decide if such a Y exists. And just as a sort of a notation abuse alert, I'm going to use R to represent both the relation and also the search problem, okay, throughout the talk. Okay. So what's an example? Well, the classical example of this is what you could call the search set problem, which is just you're given some CNF formula and you want to actually output some satisfying assignment to it, right? But as we also know, I mean, decision problems and search problems for NP are, many of them, and in the case of search set, they have essentially the same computational complexity, right? In the particular example of SAT and search set, they actually have the exact same complexity, right? This is just because SAT is self-reducible, which is, again, like an exercise that we give to undergrads. So I think for a lot of these classical NP problems, we often kind of sweep the search problem under the rug, at least when we're teaching it, because the decision and search are mostly the same. That makes sense? Okay. Well, but this is not always true. Right? And a really prominent case of where this is not true is when this relation R is a total one. Okay. So a total relation, let's remember, all I'm going to mean is that for every single X, there's going to exist a certificate, right? And I mean, there's plenty of prominent examples of interesting problems where the relation R is total. And a really common example is one I have here, right? The factoring problem. I mean, given a positive integer n, output a prime factor of n, okay? I mean, for total search problems, the decision problem is absolutely boring, right? Does n have a prime factor? The answer is always yes. But I mean, the search problem for factoring is one that, algorithms and complexity theorists and a lot of people beyond us actually really care about solving, right? So this normal perspective of kind of munging together the decision problem and the search problem for NP doesn't really make sense. It's not universal. So we actually need a theory, right, in order to study these problems, a theory that's distinct from the normal decision problem way of studying NP. And so that theory is the theory of TFNP, and the TF stands for total function NP. And what is TFNP? Well, TFNP is just the class of search problems that comes from total NP relations. Okay? And so some basic facts about TFNP. I mean, for one thing, it obviously contains P. Right? If I have a polynomial time algorithm, then I have a total relation, right? I can, it's always going to halt and output the thing in polynomial time. And also, in some sense, TFNP, you can think of it as being the functional analog of NP intersect co-NP. Okay. And in particular, as a semantic class, as sort of an intersection class between NP and co-NP, it is not believed to have complete problems, and we even have oracle separations to this extent, right? So I just mean it doesn't have a syntactic machine definition. There's no machine definition that defines NP intersect co-NP that we know of. Sorry.
What does it mean?
There's no complete problem, to say it another way. Yeah.
So how does this the TFNP equals f of NP intersect 1P work if the search problem is not a function with unique values?
Sorry, search problem is what?
What if it doesn't have a unique value? So
If it doesn't have a unique value? You mean how does the relation work?
I mean, how do we prove this equality? It sounds suspicious.
The search problem doesn't have a, if it doesn't have a unique value, I see. That's a good, that's a good question. I forget this, yeah, okay, I copied this theorem down, I forgot to write it down. Yeah, maybe we can talk about it offline, actually. This equality does hold, but I'm forgetting exactly how that happens in that case. Okay. But what I want to move on from here is just a couple, just move on to a few actual examples of problems that are in TFNP that are not obviously in NP. Okay. So to start off, let's talk with one that's probably familiar with all of us, which is a pigeon problem. Okay. And so here in the pigeon problem, we're given a polynomial size circuit. It takes input strings and it takes in n-bit strings and it outputs n-bit strings. And we're asked to output one of the two possible feasible solutions, okay? Either output a string that maps to the all zero string. So in other words, find a pigeon that maps to the first hole, or find two pigeons that collide, map to the same hole, right? And this is obviously a total relation because if the first case here doesn't hold, then there must be a collision somewhere. And in fact, there's a witnessing theorem for the fact that this is a total relation, and the witnessing theorem is very familiar to us in proof complexity. It's just the pigeoning principle, right? And so I've drawn a picture of what the actual search problem could look like here. In the blue arrows represent the pigeons mapping to holes, and then the red boxes represent like witnesses to solutions here, right? So for the first hole, the first pigeon right here is a solution because it maps to the all zero string, and then these two pigeons together map to the same hole, and so they would also form a solution. Does that make sense? Okay. So just a couple of comments on this definition in order that make it kind of interesting. So first of all, note that this input map here that we have defined, this function f, it's encoded succinctly, right, with a Boolean circuit. And because it's encoded succinctly, I mean, in particular, this means that we can verify any solution in polynomial time, right? Like I can just give you the name of a pigeon and then I can go away and evaluate the circuit. And also they're polynomially bounded because they only have, it's just the length of the string. But encoding it succinctly is what makes this problem actually interesting, right? If I just gave you the truth table of the map, then you could just brute force through and find any collisions, right? But with the actual maps encoded by Boolean circuits, well, all of a sudden, if this pigeon problem is in NP, well, then now, or is in P, then we can break any hash function, right? I mean, solving this problem is equivalent to just finding collisions in contracting maps, right? Sorry?
Or why FP here?
Why FP?
Yeah.
Oh, well, it's a function problem. Find the collision. Yeah. Actually find a collision. Yeah, function problem.
It's actually P, yeah.
Yeah. So if it's in P, then we can break any hash function. And furthermore, I mean, it's an exercise to show that if this is true, that one-way permutations don't exist even. So we should believe that this thing is hard, if we believe that these sort of basic crypto primitives that we all assume for granted exist, right? Okay, so let's see a second example. So this one's going to be called local. And so this one has a little bit of a funnier definition, but I still think it's pretty natural. So now I'm going to have two polynomial size circuits for my input. The first one, S, is going to compute what I'm going to think of as like a successor function, okay? And the second is going to be computing a potential on the nodes, okay? And the feasible solutions now are going to be any node, any string in my input, such that the potential of the successor is less than the potential of my node. Does that make sense? And so to kind of draw a picture for this, the way to think about it is to think about these two functions as giving you a graph, okay? And the way that I'm gonna define this graph is by adding an edge between two strings if two things hold. So first of all, the successor of u should be v. And second of all, the potential should be strictly greater than the potential of the node that you started with. Make sense? So with this in mind, what this is saying is that any solution then is just a node whose successor has lower potential, right? So if I think of the potential as going up, right? I've again drawn the solution. So here's two nodes. The successor of this node is this guy, but you can see that the potential is equal. And so therefore he would be a solution. And similarly, this node on the top, right? His successor is, the potential is further down. So that would also be a solution. Does that make sense? And again, this has a very simple and natural witnessing theorem associated with it. And the witnessing theorem, you can think of it as like a local minima principle, if you like. So, or in other words, every directed acyclic graph has at least one sync node. Does that make sense? Okay, cool. And just for the sake of variety, let's see one more example. So the third one is going to come from extremal combinatorics, so from Ramsey's theorem. And now the input is going to be a polynomial sized circuit. And let's think of this circuit as computing the edge relation on some graph. Okay. So I'm going to assert that this circuit's computing an edge relation. So in particular, I'll assume it's symmetric. And we can, of course, throw out any circuits that would look like, actually what we would do is we would add a violation of this to the witness, but let's just not worry about that. So let's think of this circuit as computing the edge relation on a graph. And the output is just going to be a list of n strings that encode a cliquer and independent set on this graph, okay? And of course, this is witnessed by Ramsey's theorem, which says, every graph on n vertices must have a cliquer independent set of sign at least log n over 2. Does that make sense? Okay. And again, we have a picture here. I mean, now the edges of the graph are encoded succinctly, and the idea that it's kind of hard to find, how would we come up with some way of proving the existence of this thing when the graph is essentially provided to me as not really a white box, but still we don't know how to analyze circuits, so it's very hard to imagine how we could get some handle on where the independent set or clique actually is. Okay, cool. And there's lots of other examples. I mean, we saw one which was factoring, but I mean, hash function collision is one, inverting permutations, and also a lot of problems from economics. So things like games, things like finding equilibria in two-player games or multi-party games. Problems in fair division, even things like gradient descent minimization. I mean, the list kind of goes on. All of these things exist always, but it seems like actually computing them, like actually finding them is a difficult task. Okay, so we also have a notion of reducibility in this world, which is analogous to the normal decision problem, reducibility, okay? So I'm going to say that a search problem now is many one reducible to S if it's just a mapping reduction. So hopefully everyone's familiar with this definition. So think of F as mapping inputs to inputs, and G is mapping the outputs back to outputs. And so you think of it as like, if I have an algorithm for S, well, I can start with an input X to R, map it to my input to S, solve the problem and get some solution O, and then map that solution back to a solution to R. Does that make sense? So the only thing that we require is that this implication exists in order for this strategy to work in the definition of the reduction. So this is just a mapping reduction. And now for the TFNP subclasses, I'm going to define if you give me a total NP relation, I'm going to define an associated subclass, which is just the problems that are mapping reducible to. Okay. And now let me also just make a comment. So for people who are familiar, so sometimes, especially if you read the earlier papers, this is normally defined under Turing reductions and not many one reductions. For a lot of the classical classes, these are equivalent definitions, but for some, it's kind of notably not. I'm going to stick with many one reductions through the talk because that's just kind of it's just tends to be what people seem to use nowadays. Nowadays, people are making a distinction because it seems that actually does make a difference for some classes, but I just want to point that out as a remark. Okay, great. So now that we have a notion of reducibility, well, we can actually start gathering these problems into complexity classes by picking problems of interest and then, taking everything that reduces to them, right? So here's some I've called these prominent TFNP subclasses. This is a really non-exhaustive list. It's really more like just the original subclasses that were kind of introduced and studied in the 90s. And so two of them we've already actually seen, right? So this PLS class on the left, these are just all the problems that are reducible to this local problem I just defined. So PLS stands for polynomial local search, because we're finding a local minima in a graph. And this PPP problem is just the class of problems that are reducible to this pigeon problem. Okay. And there's other interesting classes among here though. So, and maybe rather than tell you what the problems are right away, maybe instead I can just tell you what the witnessing theorems of their totality is. Okay. So I've written here, sorry if it's a little bit small, the witnessing theorems of totality for each of these problems. So in particular for PPA, it's just a version of the handshaking lemma. Okay, so all I'm going to say is if you have a graph and some node with odd degree in it, then there must exist at least one other node with odd degree. And these two classes, PPAD and PPADS, they're like directed versions of the handshaking lemma. So if you have a node in a directed graph that's imbalanced, right? If the in degree is bigger than or less than the out degree, then there must be another node that's imbalanced the exact same way. Does that make sense? And the S is kind of just whether or not you're looking for oriented sinks or non-oriented sinks. Okay, cool. And maybe just a few comments. The reason why, I mean, these classes tend to collect a lot of very, very interesting problems actually in practice. So in sort of the classical Turing machine theory of TFNP. So this class PPA, it's now known to contain a lot of these problems compared to like fair division. And this class PPAD, I mean, it contains a lot of problems related to game theory. So for instance, there's this famous paper by Daskalakis, Goldberg, and Papadimitriou who showed that computing a Nash equilibria is complete for this PPAD class. So in particular, TFNP touches like a lot of different problems, like in a lot of different areas in theoretical computer science that we should care about, right? So things like, I mean, we've already talked a little bit about game theory and optimization, but also obviously proof complexity, cryptography, circuit complexity, bounded arithmetic. These are all things that we in this room should care about. And so all these things are kind of in the halo of this theory. Yeah.
The previous slide.
Yeah.
Can you put FP as TFNP of some problem?
Oh yeah. You could say the local minima problem on trees. I think that should be okay. Yeah. Any other questions so far? Okay, great. Okay, so I'll start moving in now into what's interesting for us in this talk, I think. So that's going to be TFNP and how it relates to provability. And the root of this comes to the fact that since all of these problems are total, there must be some theorem that witnesses their totality, right? So in particular, if I pick two total NP search problems, R and S, if I can give you a many-one reduction from R to S, this is like a proof that, this is a proof of the following theorem, right? It's proving the theorem that if S is total, then R is total, right? If I have two correct algorithms and those algorithms are provably correct, right? Well, then I've just proved to you that, well, hey, if S is total, then R must be total, right? And this is the core of it. This is why this theory is so closely related to the things that we care about. And I'm going to be talking about two more or less essentially equivalent ways of formalizing this. I'm going to focus more on the proof complexity side of things because it's proof complexity workshop. But I am going to talk about the bounded arithmetic a little bit at first because I think there's a lot of older papers that kind of do it this way as well. Okay. Okay. So let's just talk briefly about the bounded arithmetic approach. So let's just start by picking some base theory that captures FP. So for instance, we can pick PV or S12. I think for these kinds of things I'm going to talk about doesn't super matter, although I'm happy to be corrected. And let's remember that a sigma B1 formula, this is just a formula of the following form. It just has a single bounded quantifier attached to some formula over our base theory, right? And for those who aren't experts on bounded arithmetic, like me, let's just remember that this T, we should think of this T of Z as giving like a polynomial bound on the description length of X, right? And so in particular, what this means is that these types of formulas, they capture exactly the NP predicates, right? We're just asking, given an X, or in this case, given a Z, find some X that witnesses that this thing is true. Does that make sense? And in particular, the X should be should have a description length that's polynomially bounded. Well, and if the sigma B1, oh sorry, this typo there, it should be sigma B1. If the sigma B1 formulas are exactly the NP predicates, then the true for all sigma B1 sentences are just the total NP search problems, right? I'm just asserting that one of these predicates is total. Does that make sense?
That theorem was actually a decade earlier.
Oh, thanks. Yeah, okay. Yeah.
Happy to get my name on it, but it was Stockmeyer and Rathwell.
Stockmeyer and Rathwell. Okay, thank you. Yeah, so this is, yeah, okay, thank you very much. Maybe I shouldn't have recorded. Okay, cool. And so now with this, we have a natural question associated with this. Again, I'm not an expert at bounded arithmetic. I'm very happy to have these corrections. Please tell me. So in particular, we can now ask this question, if T is a theory of bounded arithmetic, well, what are the actual for all sigma B1 consequences? And maybe it shouldn't surprise you that the answer is a subclass of TFNP, right? The true theorems are going to give you a collection that are basically going to correspond to a subclass. Okay, so let me give a couple of examples of these characterizations. So if you start with just like a base theory like PV, well then the consequences are going to be exactly the things that are computable in FP. And if you start walking up this TI hierarchy, so just by adding in induction on these sigma BI predicates, then you start capturing actually interesting TFNP subclasses. So in particular, sigma B1 induction corresponds exactly to this class PLS that I was just talking about a few minutes ago, the problems that are reducible to local, okay? And there's a little bit of, you have to be a little careful whether I'm talking about Turing reductions or many one reductions here. Luckily for PLS at least, they're the same definition, so let's not worry about it too much. But then yeah, it turns out that as you go up in the TI hierarchy, you can define capturing problems. Many people in this room have been involved in these kinds of theorems, showing that there's interesting TFNP subclasses that capture these sorts of things. Okay, cool. So let's talk a little bit about actually separating TFNP subclasses. Well, we have this problem, right? Because since FP is contained in TFNP, which is contained in NP, if I could give you any separation between two TFNP classes that are, above P, well, this would immediately tell us that P is different from NP, right? So, we can't really expect to separate these classes without making some kind of breakthroughs. I mean, also equivalently, we don't know how to separate the strengths of these corresponding bounded arithmetic theories without some additional assumptions. And so the question is, what can we do? Like, how can we actually test the strength of these things, right? How can we try and get some understanding of how these theories relate to one another? And the answer is, I mean, one answer, and a very popular answer, is to start thinking about relativized versions of these theories, right? So, and this is going to be the focus of pretty much the rest of the talk. So in black box TFNP, what I'm going to call black box, sometimes this is called type 2, the type 2 theory. Instead of the input as being provided by a polynomial sized circuit, I'm now going to think of the input as being provided as like an oracle that you get to query. So for example, I mean, if you take this pigeon problem, now the function f that we got, we'll just think of it as being provided by query access. And the goal is to, find some collision in this contracting map from n to n minus 1. Okay. And of course, I mean, it's how many queries does it take to solve this problem? Well, this is just a decision tree lower bound at the end of the day, right? A decision tree adversary could just keep mapping pigeons to holes and a matching, and just force the very last pigeon to find a collision. So this problem, at least in the black box world, is hard. Yeah.
Did you find it slightly different to previous?
Good. Yeah. Good. I'm glad you caught it. Yeah. Yeah. So I did define this problem very slightly differently than before. So before I had a something mapping to, hole 1, and I was calling that a witness. These two problems are equivalent.
Mm-hmm.
So the way to do that is to just, redefine your circuit by just, if I map to hole 0, map to hole n or something like that. Okay. So that's that's one way to show that these are equivalent. But one kind of nice thing about the black box theory is that if the inputs are defined as black boxes, I'm now get a lot more control over what the input looks like. So I don't need to worry about these extra syntactic at least when they're easy to detect. So, okay, so, you know, as a time-honored complexity theory tradition, we're going to study the black box setting instead of studying the setting where we would like to know the answers, I guess. Okay. Well, what does this mean for bounded arithmetic? You know, we can always translate all these questions back into the bounded arithmetic setting. Well, now this just corresponds to separating the relativized theories, right? So what you can do is you can add in sort of an uninterpreted predicate symbol, call it alpha, to each of these theories. And all of these equivalences that I mentioned on this slide before, they also carry over in this relativized setting, right? So separating these relativized theories is just equivalent to providing black box separations between the classes. Okay, and I'm continually saying black box, but again, if you read the literature, this is often there's this other notion of like type 2 complexity. When I'm saying black box, this is just kind of the non-uniform analog. Don't worry too much about the distinction. It's just whether or not you think of the oracles as being provided to you uniformly or not. Okay. Well, now that we're trying to separate relativized theories, well, now we can start bringing proof complexity, right? Because as you know, many people is well known, right? Like well-behaved theories of bounded arithmetic correspond directly to propositional proof systems. And providing separations between the corresponding proof classes are kind of really great ways to separate the strengths of these theories, right? So one example of such a characterization is that if I take this T12 alpha, which corresponds in this case to black box PLS, right? Well, if T12 alpha proves some you know sigma B1 predicate now with this additional symbol, well, it turns out that this means that there's a low width resolution refutation of this propositional translation. Okay, so what this should translate to is that if I want to separate the theory, all I need to do is prove a lower bound on resolution width, which is, I mean, we're machines at proving these kinds of things, right? And so in particular, what this means is that proof complexity lower bounds imply black box separations between TFNP classes. Cool. So probably the first paper to study this systematically, like the sort of relationship between proof complexity lower bounds and TFNP subclasses, was a paper by Beam, Cook, Edmonds, and Pagliazzo and Patassi back in the 90s. And of course, they phrased everything in this language of type 2 complexity that I was saying a second ago. And they showed separations between lots of the TFNP classes at the time. So the new ones that they separated here, I've just drawn, I've highlighted on this diagram. Okay, so some of these separations in particular were proved directly just by looking at, you know, oracle reductions to classes and trying to prove direct separations between things. While others, more intriguingly, and in particular, this separation between PPADS and PPA was proved using a Nullstellensatz effect. Okay. Okay. And so this is kind of a hint that proof complexity can play a bigger role in understanding the black box complexity of these classes. And follow-up work only a couple of years later by Baresh, Oppenheim, and Morioka made this connection between black box relationships and provability a lot more, like they brought them a lot closer together. So roughly speaking, without getting too into the definitions of what they proved, what they showed is that if you take two of these black box TFNP problems, and let's suppose that the totality of these problems can be expressed in a particular way. So let's not worry too much about it. It's a existential formula over first order in first order logic. Okay, and it should be a finitary principle, but let's not worry about that too much. And then, so what they showed is that if the search problem R reduces to the search problem S, then there's actually propositional proofs of this theorem. If I start with a propositionalization of the fact that S is total, then you can prove in depth 1.5 tree like LK, or they also showed in Nullstellensatz, that if S is total, then R is total. Okay. And in particular, by proving this theorem, they were able to get some even more separations that weren't known at the time between these TFNP subclasses. So particular between PLS and PPA, and among a few other more technical separations that were subsumed by later work. Okay, now this theorem was improved again by people in this room and probably online. So in particular, Buss and Johnson back in 2012 improved this theorem to show that it even held if you have Turing reductions. And Moritz-Müller showed sort of a bounded arithmetic type strengthening of this result, which showed that actually even if you have consequence over a particular theory for all T2 alpha, which is much stronger than just saying Turing reductions, then still you can prove this kind of propositional translation. Okay. So the lesson here is that, hey, if this is a very specific and a very formal representation of this sort of hand-waving theorem I said a little while ago, right? If I have a many one reduction from R to S, then I actually have a proof that of this theorem, right? That if S is total, then R is total. And it's in fact a propositional proof. And so propositional separations, therefore, should imply, non-reducibility. Okay, so now let's now's a good time to take a pause and maybe answer any questions. And I'm going to start moving into some of the more recent work. Okay.
When you talk about many one reductions in the black box setting, you mean query complexity. You don't chart
Query
internal computations.
That's great. I'll give you a formal definition in a second. Any questions? Okay, great. So recently, there's been a lot of recent work that's been sort of revisiting these relationships. So a lot of these theorems that I told you were proved in the early aughts in the 90s. The bounded arithmetic proofs have been going all the way through, but the relationship between proof complexity, these kind of separations go back to the 90s and the early aughts. And recently we've kind of revisited this, in particular in light of the lifting theorems. The lifting theorems in communication complexity really kind of led us back to understanding this theory. And this led to a bunch of new results and new characterizations. And for the rest of this talk, I'm going to survey some of these. Okay. But first, let me answer Sasha's question and give a formalization of what I mean by black box TFNP. Okay. And I'm going to give a non-uniform formalization. So normally we use this type 2 complexity, but this non-uniform formalization makes it cleaner to go to the proof, just the proof complexity setting directly. Okay. So just quickly, a query total search problem is going to be a sequence like this. So it's just going to be a sequence of relations R. So now the input is an n-bit string on each n, but I'm going to let the output set be kind of whatever you want, just any polynomial size. Okay, we're in the query complexity setting, so I'm not worried about encodings too much anymore. And now the idea is that I'm going to say that this search problem R is in black box TFNP, so that's what the DT stands for decision tree. If this predicate, Rn, for a fixed output O, right, for a fixed solution, can be computed by a polylog n depth decision tree, right? So in other words, if you give me the name of a solution, I can verify with only polylog many queries if that solution is good for me. Does that make sense? So for example, if you want to take the pigeon problem, right? If you give me a collision, if I say, hey, I claim to you that these pigeons are colliding, you can verify that just by querying the first pigeon and querying the second pigeon and making sure that they both map to the same thing. Make sense? So that's only 2 queries, in particular, way less than polylog n.
The output space was exponential before, polynomial size now.
It was, the output space was, yeah, this is good. Now I'm restricting you to be polylog n many queries, so it is still exponential.
So you basically just, you all the way when you started to do f to n minus 1, you scaled down from n-bit strings to the numbers 1 through n, and that's sort of been going on for a few slides now.
Yes, so I have like 2 to the, so if you have like a string, like 2 to the n strings, I was still asking for polynomial time computation. So if n is 2 to the n, then polynomial time is polylog of 2 to the n. Does that make sense? Yeah.
But I mean, exponential will be quasi-polynomial, right?
Exponential is quasi-polynomial, sorry?
This is depth,
This is depth.
so that's time.
Yeah, that's right. So this is, so now our upper bounds will be quasi-polynomial time. I guess that's maybe that
You also scale down the size of the input.
scale down this, I scaled down the size of the input to n bit strings. Well, it's still polynomial in it. It's still everything like that.
I still don't
Yeah,
understand how it works.
so now it's you've mixed up the 2 things. So way.
So. No, I think this is okay.
Oh, no,
No, this is okay.
No, you're right.
This is
you're
okay,
right.
everything's okay, everything's okay.
Right,
I haven't scaled down the size of the input or anything. No.
No, the input was a circuit.
Before
on
the input was
ambit,
a polynomial size circuit, right?
But it was polynomial, yeah.
Yeah.
Why is it important that ON is polynomial size? It does not look quite natural.
Oh, yeah, that's a good question. Maybe I should have put quasi polynomial size, but maybe it'll make sense.
Even if it is exponential in N, also binary strings of
I
length.
guess exponential and
Also strings of length.
maybe I'll say that this will be like without loss of generality, it'll turn out. But yeah, that's a good point. Maybe I shouldn't have made that prescriptive, but once I connect it to proof complexity, it'll make a bit more sense. I'm gonna encode this as a formula, and then that'll give an upper bound of the size of the formula. Any other questions? Yeah, sorry if there's a bit of confusion with this translation here. Okay, so let me give you, maybe I'll give an example which will hopefully sort of clarify things here. So here's sort of the canonical example that you should keep in your mind, which should be very familiar with to proof complexity folks. So if I start with an unsatisfiable CNF on M clauses, this gives me a very natural query total search problem. And that's this S of F, which just is the following, right? Given an input X and the name of some clause I, I'm gonna accept if that clause is false when I evaluate it on X. Okay. And so in particular, if I have a sequence of unsatisfiable CNFs, then I'm gonna let S of F be this corresponding collection of search problems. And this is just this false clause search problem, right? Given an input X, give to me a false clause of X, right? So I mean, these kinds of problems are solved by DPLL and CDCL solvers all the time, and they played a big role in understanding lower bounds of proof complexity. And so this is where this comment about the number of certificates comes from. So this S of F problem is going to be in TFNP if these formulas have polylog n width. And if they have polylog n width, then that puts an upper bound on how big they're going to be. There's only going to be at most quasi-polynomially many different solutions. Does that answer your question?
But I mean, you said it is polynomial though.
Yeah, that was a typo. It should have been quasi-polynomial. Yeah. Yeah. Okay. And the reason why this puts an upper bound in general is because actually this search problem example is canonical. Like if I give you any query total search problem in TFNP, then actually there is a false clause search problem that is equivalent to that search problem. And you can express it like this. If I start with some query total search problem in TFNP, then you can consider the following CNF formula, which just says that R of n is not total, right? I take the conjunction over every single solution to this search problem, and then I'm going to say, hey, okay, this is actually not a solution, right? And now I can express this Rn of x, as a decision tree, right? As a low depth decision tree. So in particular, this whole thing can be expressed as a low width CNF formula. Does that make sense? And so in fact, these things are actually equivalent. I mean, it's not hard to see that if you solve this search problem, well, then I'm just telling you the name of a clause that's false, and therefore I can recover a solution to my original search problem that's false. So these things are totally, this false clause search is actually like totally canonical for purposes in the black box setting. Yep.
So maybe so if my Rn is basically the is the analog, like suppose my relation is factoring or something like that.
Yeah.
So what happens here?
Yeah, okay, so what happens here? So what we're gonna do is we're gonna go, let me just bop back a little bit. So remember that I asserted that these Rn's can be computed by polylog n depth decision trees, right?
Yeah.
So for each fixed O, I can express this as a decision tree. So what I'm gonna do is I'm gonna take that decision tree and I'll just write it as a CNF and just plug it into that conjunction there.
In factoring, you cannot do it.
But for factoring in particular, it doesn't really make sense because, yeah, expressing factoring in this way doesn't really, yeah, I mean.
Yeah, so I see,
Yeah.
so it doesn't.
Factoring, yeah, there's this whole question of like these natural TFNP problems like factoring, ones where the input isn't a circuit. These don't really fit into this model super duper well, to be honest, yeah.
Okay.
Yeah, because you would have to be providing the number kind of bit by bit. And then you'd be asking, well, how many bits of the number do I need to query? And you have to query all of it, right? Like it's kind of not super natural.
I see, so that doesn't, okay.
It doesn't, the factoring in particular doesn't super fit into this model super duper well. Okay.
So here your decision trees are polylog depth, right? Not
Polylog depth, yeah.
Not
Not width. Wow, oh my god, I'm normally so much better with typos, thank you, yeah. Polylog and depth decision trees, yeah. Any other questions or corrections?
As many weaknesses as you have. Decision to use its count.
Okay, cool.
Okay.
Okay, well, now that we have a notion of black box problem, we can now talk about black box reductions. And a black box reduction is just a many one reduction, like something we've already seen, except now it's going to be computed by a low depth decision tree, right? So now I'm going to say that R of n reduces to S of n if there's two functions, f and g, that still satisfy this mapping relation, right? However, every single output bit of these two functions should be computable by low depth decision trees, right? So if you give me an output bit with only polylog n many queries, I can figure out how many, like what the actual answer to that bit should be, right? And now here's a little bit of a funny thing in this definition. I'm going to define the complexity of this reduction to be this joint measure, okay? It's going to be d, which is the depth of the decision trees, plus log m. So notice that this m here is this m right there, right? Yeah, so the m is the index of this search problem S right here. And the reason that we have to have this joint measure is because sometimes your problem S is rich enough to be able to simulate a decision tree by itself inside the problem, right? And so what I could do is I could just embed the decision trees into S and then just have like a depth 1 reduction or something silly like that. So I need to actually, all I'm saying is that I need to give a reduction to not to like a small instance of S, not like an exponentially large instance of S. Does that make sense? Okay. And so again, in analogy with the white box setting, and also to remove black boxes to make ourselves feel better, I'm gonna just write less than or equal to m, right? To mean that there's a polylog n complexity reduction. Okay, is there any questions about this?
You've got two different m's there, of course, here.
Yeah, different. Yeah. That one I feel less bad about.
Yeah. Yep.
Okay, cool. So let's just see an example. So if we go back to this local problem that we saw a couple slides ago, well, if I have a function s, so I have these two functions s and p, and now if the feasible solutions again are just going to be exactly the same, in this PLS to the DT class, it's just going to be the class of all the total query search problems that are reducible to this. Okay, cool. When do I have until, just so that I 10 or is it like 9:50 or something like that?
No.
Including questions.
10? Okay, cool. Okay. All right, so let's talk about let's think now about the proof complexity of this PLS. So this people who've been paying attention, I mean, this also follows from the bounded arithmetic thing I said a second ago. So each search problem in this class corresponds to a polylog n with sequence of unsatisfiable CNFs, right? We can write it, here's the CNFs, they look like this. And we can ask, what is this family of CNFs? And the answer is just exactly those with polylog n with resolution refutations, right? And so in particular, to prove that I'm not in here, you can actually just prove a width lower bound on these formulas. And so I was originally going to prove this. So maybe just in the interest of time, I'll just state the theorem and then move on to some of the new results. So in particular, if I start with a sequence of unsatisfiable CNFs, and I consider the sequence of search problems that comes from it, then this sequence of search problems is in this PLS class if and only if this sequence f of n has low width resolution refutations. Okay. So this is just a proof. I'm happy to talk about it offline if anyone wants to see it, but maybe I'll just skip over it in the interest of time. And I'll move on to the next question, which I think really comes out naturally from this, which is if resolution corresponds to a TFNP class, and both of these things are very natural objects, resolution proofs and PLS, what other proof systems can we characterize in this way? Okay. And so I'm going to introduce a little bit of notation. So if P is a propositional proof system, and if C is a subclass of TFNP, then I'm going to write C sim P if just this conclusion holds. So S of F is in this class if and only if P has efficient refutations. And now I'm going to put a star here next to efficient, right? Often efficient is going to mean like low width or low degree or low depth, not just polynomial size, which is something to keep in mind. It's a good thing for us because those are easier to prove usually. And now let's look back at the sequence of the classical TFNP subclasses and take a look at what corresponds to what. Okay. Well, these two we kind of already talked about, and in particular, these two characterizations follow from the bounded arithmetic results that I said at the beginning of the talk, right? So PLS corresponds to narrow resolution, and FP corresponds to decision trees or shallow tree-like resolution, low depth decision tree, low depth resolution. But in the recent work, we've also been able to find that these other classes also correspond to proof systems that we actually like. So this class PPA corresponds exactly to F2 null-Stellensatz. So in particular, a search problem is in PPA if there's a low degree null-Stellensatz refutation. And this PPAD corresponds to low degree integer null-Stellensatz with the caveat that the coefficients are written in unary. Okay, in order to be small, that I can measure them. You can actually come up with a class for binary null-Stellensatz too, binary encoding too. It's a little weird, but it is possible. And this class PPADS, well, it's also another interesting class. It's low degree unary Shirali-Adams. Okay. So in fact, even though these classes have been sitting around since the 90s, it turns out that for us, they correspond to proof systems that we have been studying also since the 90s. Okay, and I've also left something out, and that's this PPP. So you can ask, what is the proof system for that? And the answer is, I don't have a natural answer for you. Like I don't know, there's no proof that I know of. It's an open problem to pick a proof system off the shelf and be like, hey, this is equivalent to PPP. I kind of believe that there is no such natural system because PPP is a little bit less robust than these other classes in certain senses that I don't want to get into right now. But it's an interesting question to come up with a natural system. You can come up with an artificial system that characterizes PPP. And maybe I'll talk about that now. So when are these characterizations actually possible? Well, Buss, Fleming, and Apeliazo just a year ago, 2 years ago, came up with necessary and sufficient conditions, okay? So in particular, the proofs that you're looking at, they must be closed under low depth decision tree substitutions. So in particular, if I have an efficient proof, I should also have another efficient proof of the same formula if I plug in a low depth decision tree for every variable, right? This corresponds to the fact that I use low depth decision trees in the reductions, right? And also, P must prove its own soundness. Okay, there must be a proof of the reflection principle for P, particularly suitably encoded as a propositional formula. Okay. And so there's lots of examples of these. This is not actually a terribly restrictive list of properties, right? So here's a list of proof systems which satisfy these, and all of these correspond to TFNP subclasses as a result. So bounded with resolution, if I take bounded depth Frege, as long as I add polylog n depth width on the bottom layer, you get a characterization of that as well. Bounded degree null-Stellensatz over whatever field or ring you like, as long as it's complete. Bounded degree PC, Shirali-Adams, sum of squares, etc. So all of these things satisfy these two properties.
Bounded degree here means polylog.
Polylog degree, yeah, not constant degree. Cool. And it's also important to note some non-examples, okay? A really prominent one is resolution. That is with high width, right? If I plug in a low depth decision tree to a wide clause, that's going to blow up the size of the proof exponentially, right? So we can't capture high width on the bottom in this way. So, and this also of course carries over to high degree variance of these systems. Another interesting example is cutting planes. Cutting planes does not survive decision tree substitutions. You can formally see this by the lifting theorems for cutting planes. And I also put another one, which is probably true, but I don't actually know how to prove it. Lovász-Shriver, at least degree 2 Lovász-Shriver should not survive substitutions under bounded depth substitutions. Yeah.
What about proving its own soundness, you know, I mean, I thought resolution would have problems with that, and what about? Okay, can you go to the previous?
Yep,
Bounded with resolution can prove its own soundness?
it
That's
can,
what
yeah,
you-
suitably encoded. Yeah, you have to encode it the right way, but yes, it can, yeah. Yeah, the details are in Sam and Noah and Russell's paper
Oh,
Yeah.
about.
about how to
bounded
do
with-
that. Yeah, bounded with resolution. Yeah.
You just need the like reflection principles encoded at like low width.
So where does this lead? Well, in particular, it leads to characterizations of algebraic and semi-algebraic systems. We get new black box separations, and we also are going to get new proof systems and new separations of proof complexity. And what's also interesting is that some new stuff that's come out of studying this are what I'm going to call like structural proof complexity. We learn new structural relationships between proof systems that didn't really exist, that weren't obvious before. So I'm going to hopefully have time to give a couple of examples. So let's start by talking about the new separations. So after all this work on black box separations before, the only remaining separations between these classical TFNP classes were these ones here in the black box. Okay, so it was unknown whether or not PLS was contained in PPADS or in PPP. Okay. And of course, if we translate it using this characterizations that I just said to you, it boils down to answering the following question. Okay. So whether or not unary Shirali atoms can actually simulate resolution efficiently, bounded with resolution. And now, of course, Shirali atoms can simulate bounded with resolution, but that's going to cause an exponential blow up in the sizes of the coefficients. If you look at the naive simulation, you get this exponential blow up in the depth of the proof. So it was an open question whether or not you can do this without paying that blow up, and that's equivalent to separating these two black box classes. And so 2 years ago, we were able to actually separate these. So we showed that in particular, if you just look, well, this isn't exactly what we proved, but it's equivalent to what we proved. If I take any low degree Shirali atoms refutation of the non-totality of PLS, so the non-totality of this local problem, then the coefficients necessarily must blow up. So there are high degree refutations of this that do require, that do use low coefficients. But if I want the degree to be low enough to be in the simulating the resolution kind of regime, then you're going to pay this exponential blow in magnitude. You can't avoid it. Okay? And as a corollary, we can separate this PPADS from PLS. And it turns out that by just kind of generalizing the earlier techniques that came from these 90s works, you can actually show that this directly implies that PPP is not contained in PLS. Okay? This was also noticed by Ilario and Neil. And after this, there's been kind of a bunch more black box separations that have been used in this setting. So Noah, just immediately after me, is going to talk about using proof complexity to separate the Turing closure of the pigeonhole principle from the pigeonhole principle. Neil later is going to talk about using proof complexity to separate intersection classes. And also in very recent work, we can use proof complexity to show that that Ramsey's theorem doesn't reduce to pigeon, so it's not contained in P. And so in my last couple of minutes, let's talk a little bit about the structural proof complexity that I alluded to a second ago. And I want to get to this by first starting about a new search problem that you can compose out of any old search problems, okay? If you give me two NP search problems, R and S, I'm going to define this problem either R of S, which is the following. You get an input to both, and I'm asking you to solve either one of them, okay? And it's not hard to verify for yourself that either is complete for the intersection of the two classes, actually. So a search problem is going to reduce to either if and only if it reduces to R and it reduces to S. Okay. And as I said earlier, like this is an unusual thing in complexity theory, right? Like if I take the intersection of two complexity classes, this is often a natural thing to do, but it's never syntactic. Right? Like NP intersect co-NP is widely believed not to have complete problems, but yet these TFNP subclasses are syntactically well behaved. If I take their intersection, there is a complete problem. So we should ask whether or not these things are natural, and it turns out that the answer is yes, actually. So for instance, there was this just a couple of years ago, there was this cool breakthrough by Fernley, Goldberg, Hollander, and Savani, who showed that PLS intersect PPAD is equal to this class CLS for continuous local search. And you should think of this as being the problems reducible to the totality of gradient descent. And there's a lot of interesting TFNP problems that lie in this intersection, and it turns out that there's actually a good reason for this. There's a very natural complete problem. Okay. And this paper kind of opened the floodgates for these kinds of intersection collapses, actually. So in a follow-up work with some other folks, we kind of improved this collapse to the end of potential line class. And we also proved an analog for the sync classes. And recent work that you're going to see Neil talk about later is actually characterizes like all the intersections between the classical TFNP classes. Okay. And this, of course, raises the possibility of defining intersection proof systems, right? So I'm going to say a proof system is the intersection of two other proof systems if it has a short proof in one, if and only if it has a short proof in the other two, right? And it turns out that you can do this actually, which was to me quite a surprise. So if you just take this PLS and PPADS, which I think is one of the most natural examples. So PLS corresponds to narrow resolution and PPADS corresponds to unary Shirley atoms. And it turns out that their intersection corresponds to a proof system that I'll call reversible resolution. Okay, and this is very closely related to max-sat resolution for people who are familiar with this. So now you have two rules which are applied with substitution. So I'm going to actually delete a clause when I apply a rule to it. And the rules are symmetric. I can resolve C or X and C or not X, or I can undo that. I can go from C to C or not X. And it turns out you have a short proof in unary Shirley atoms and resolution if and only if you have a short proof in this reversible system.
So by substitution, you mean these, the usual thing you think about, for example, in a tree-like system is anything you derive that wasn't the input gets erased. So are you erasing inputs too, or no?
You can reuse inputs if you
can reuse inputs.
You can, yeah.
So this is basically a tree-like,
It's a tree-like
proof system with these two rules.
Exactly.
So because substitution usually means something else.
Exactly. Yeah. Sorry, maybe substitution wasn't the best word. You should think of this as being like a tree-like proof system, but the reason that it's different is just entirely because of this weakening rule, because it has two outputs now.
Right.
Yeah. So it's not a tree-like. It's not actually a tree. Yeah. And I don't know. So just for the sake of putting it down, here's a picture of all of the non-trivial black box intersection classes. So when I write this picture, all of these classes have their own complete problems. And there's black box separations between every single pair of them. Okay. The red systems were considered by Neil and his co-authors, but not in our paper. And also all of these subclasses have corresponding proof systems, which you can think of as being kind of like fragments of resolution. Except for these red ones, these things involving PPP, because again, we don't really have a proof system for PPP.
Do these intersection theorems translate to the original TFNP classes?
Oh yeah, they're true for Turing machine TFNPs too. Oh yeah. All these intersections we have complete problems for the classical versions. Yeah.
But they follow directly, or you need a new proof for that?
No, it's the same proof. I mean, they're low query reductions, but they're uniform enough that it's the same proof. Yeah.
So the label on top probably shouldn't be PPP.
Oh yeah, you're right. Thank you. Sorry, not PPP. So sorry, two of these arrows don't exist here. Sorry, these are not arrows. Sorry, typo. This is what happens when you're fixing your slides on a red eye. Okay. So I'm running low on time, so maybe I'll leave this slide to Neil's talk for later. It turns out that maybe I'll just scan through. So you can also characterize, it turns out, the joins of classes. So this corresponds to solving both of the problems rather than the intersection of them. And we can get some interesting results for this involving Null-Stellensatz, but maybe if someone's interested about that, we can kind of talk about it offline. And maybe I'll just skip ahead to the summary here. So the kind of executive summary of this is that TFNP, we should think of it as being an algorithmic counterpart to proof complexity and bounded arithmetic. And separations between these systems usually equivalent to separations between the TFNP subclasses. And in particular, there's benefits to studying both sides of this theory. Okay, so we get black box separations from the proof complexity side, and the TFNP side gives us interesting new structural theorems inside proof complexity. And I think that these structural aspects are really particularly exciting. They gave me at least sort of an organizational principle to think about what classes should exist and what classes should not, if that makes sense. Like, why do we see the proof systems that we see? You know what I mean? And where are the other ones in some sense, right? This kind of tells you like, oh, well, there's natural search problems and these proof systems correspond to these natural classes. So it makes sense that they should have popped up at some point, right? To me, it kind of helps organize the landscape of potential proof systems in this way. And so I have a couple comments on next steps, but I'm running out of time, so maybe I should just cut.
The final comments.
Final comments? Okay, cool. Yeah. So let's talk about what I think the next steps for this kind of theory is. The most obvious one that people are probably thinking about is, can this lead to progress on boundary questions, right? The famous boundary questions in proof complexity. I mean, so one obvious question is separating the bounded depth Frege hierarchy with respect to a CNF. This has been considered in bounded arithmetic and was one of the original reasons for looking at all these characterizations in the first place. But I think there's also other interesting questions that you can ask here. So I mean, lower bounds on res parity, like with the recent regular resolution lower bounds, or AC0 mod 2 Frege, like these should have corresponding TFNP subclasses, at least AC0 mod 2 Frege should, because it's certainly closed under decision tree reductions. Res parity is not, but you could take its closure, right? And you can ask about these proof systems and see if there's any kind of way of interpreting it in this setting. We can ask about strong proof systems, like can we use this to generate more interesting combinatorial principles for Frege and extended Frege? And there is, again, some work in this on the bounded arithmetic side of things. And you know, it's a long-standing open problem to find hard tautologies for these systems, right? And so maybe we can kind of use some of these structural ideas to generate new and hard tautologies. And so finally, and also there's these outlier TFNP classes, so things like Ramsey, which are not really known to collapse in, like they seem to be a little bit orthogonal to these classical TFNP classes. And there's lots of very weak TFNP classes that get studied in the classical theory that, to my knowledge, haven't even been looked at in the proof complexity setting. And so it's very natural to ask if there's any kind of black box separations that we can make down there. And okay, so maybe I'll just finish with this with a conceptual question. And it's something that I'd really like to answer just for myself. Can we qualify? Can we give some kind of qualification as to why some search problems give rise to very natural proof systems? So for instance, like PLS gives rise to narrow resolution, while others don't, right? What principle, what property of a search problem makes it robust in this particular sense, that gives it a good proof system? I really don't have a good feeling for this. I thought it was Turing closure, but it turns out it's kind of not. Like, I'm sure Noah will have, we'll talk a little bit more about that. Anyways, yeah, thanks for listening, and sorry for going a little bit.
We already had a couple of questions, but any, like one or two questions more for Robert before we break for coffee? Comments?
Can you give an example or two for these very weak TFNP?
Oh yeah, so a lot of them are related to these a lot of them are related to algorithmic questions for these like things like parity games. So there's a lot of like finding winning strategies, like computing winning strategies for particular infinite two-player games, stochastic games, parity games, these kinds of things. They're all way inside PPAD. In fact, inside the subclass of PPAD. In fact, inside the CLS subclass. And so it'd be interesting to wonder, you know what I mean? Is there anything interesting about studying the black box? These things? Yeah, no.
Doesn't Sam's paper sort of give an answer as to like natural proof systems when it comes to these like Turing closures?
How so?
I thought you could interpret Sam's paper as showing there's like no real natural proof system, like say depth 1.5 Frege plus like a principle when the TFNP class is not Turing closed.
That's true, but I mean, you also know that you can write down a proof system, right? Like what this boils down to for Turing closures is that like you can propositionalize this result very simply, like the Turing closure of PPP is actually a pretty natural system. You get tree-like resolution, except you get to use divisional principle for free, right? But it would be nice if there was, I don't know, like a more like a, I mean something a little bit different than that, right? I mean something more like resolution, right? Something where the lines are natural objects and we deduce new lines from old ones, or we do some sort of algebraic manipulation, right? Like some of these are clearly more natural than just proof system plus a new axiom, right? And so I'm wondering about those.
Yeah.
So let's thank Robert again.